Section 5.4 deals with the definite integral. Now, the definite integral is used to compute area under the curve, probabilities, average value of a function, and many other things. So what we're going to do is just start by trying to figure out, well, how would we compute the area under a curve, and then lead us to the definite integral. So let's say that I give you this function right here, and let's call this function f, and I asked you, well, tell me, what's the area from A to B? Well, looking at this function right now, I have no idea, because I don't know how to find the area of this green figure, because it's not something that I'm used to from geometry. But I know how to find the area of a rectangle. So if I just make this into a rectangle, I could find the area of this rectangle here, which would end up being just an overestimation of our area under a curve. Well, remember, the area of a rectangle is our length times width. So in this case, my area would equal width here, which is b minus a, times my length here. Well, that height is f of b, so times f of b. So I could say, okay, well, I'm just going to approximate that area using that big rectangle there, and it's going to be whatever b minus a times f of b is. Well, again, looking at it, that's really an overestimation. That's almost probably going to be double what the area actually is. So one way I could try to make this a little better is to add more rectangles underneath the curve. So again, if I'm calling this function f, this a and this b, I can break this area up into different subintervals. Let's call this x sub 1 and then this x sub 2. So then I could use the sum of all three of those rectangles to try to approximate the area under the curve. So for this particular function here, I would say that my area is equal to, it's always going to be length times width, so here it's going to be whatever x sub 1 minus a is, times f of x sub 1, plus, well, my next one, which is going to be x sub 2 minus x sub 1, times f of x sub 2, that height here, and then finally plus b minus x sub 2 times f of b. Now, another way that I can write this is if I say, well, I'm just going to make these rectangles have equal width, and if I'm making the rectangles have equal width, then the distance from here to here should equal the distance from here to here, which should equal the distance from here to here. Well, since I have three rectangles that I'm looking at here, the change for those rectangles is going to be b minus a all over 3, right? So b minus a over 3 would give me the width of each one of those rectangles. Therefore, I could really write this as my area is equal to b minus a over 3 times f of x sub 1 plus b minus a over 3 times f of x sub 2 plus b minus a over 3 times f of b. And I could take it a step further if I wanted to and say, wow, well, I can just factor out this b minus a over 3 from each one of these terms. Therefore, my area could be written as b minus a over 3 times the sum of f of x sub 1 plus f of x sub 2 plus f of b. Well, now we're going to look at it with the left endpoints. What's the difference between the right endpoints and the left endpoints? And for all two of these, we used right endpoints. We looked at the right endpoints of our rectangle. We're going to do again the same thing, but now we're going to find the area looking at a rectangle with left endpoints. So we're going to call this f, and here's a, and here's b. So we're going to look at this rectangle right here. The area of this rectangle is going to be b minus a times f of a, because now my height, or that length there, would be f of a. Well, what about this one over here, this curve. Again, this is F, and we're looking from A to B. Well, notice what I did for this one is I said, okay, well, let's add in more rectangles. So now I have 1, 2, 3, 4, 5, 6. So I broke myself up into 6 rectangles of equal length. So each one of those is going to be b minus a over 6. And this is the point x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. So if I'm using my left endpoints for this area, recall I can factor this out. It would be b minus a over 6 times the sum of those left endpoints, which would be f of a plus f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus f of x sub 4 plus f of x sub 5. We would use our left endpoints for each one of these rectangles to find the estimate of the area under the curve. So now, the area under the graph of a function can be found as follows. If f is a non-negative continuous function on a closed interval, so f is non-negative and it's a continuous function on a closed interval, then the region under the graph of f is f of x sub 1 times delta x plus f of x sub 2 times delta x plus f of x sub 3 times delta x all the way to f of x sub n times delta x, where delta x is equal to b minus a over n. X sub 1 all the way to x sub n are arbitrary points in n subintervals of equal width. So each one of these is that height or that length. And then that delta x is your width of b minus a over n, depending on the number of rectangles you choose. Now, above we used left endpoints to find our area and right endpoints to find our area. But if your function is positive and it's either increasing or decreasing on that closed interval, then the left and the right sums, we're going to approach the same number as n approaches infinity. So the more rectangles that you get underneath that curve, the area that you get using the left endpoints and the area that you get using the right endpoints give you the same answer. So let's practice finding the area under a curve using left and right endpoints. So it says divide the interval 1, 4 into 3 equal subintervals. Then draw in left and right rectangles and compute L sub 3 and R sub 3. So we're going to do my left here and my right here. It's telling me that I'm looking at the area under the curve, under this given curve from 1 to 4. So we're looking at this area right here. And I want to take this interval and divide it into 3 equal subintervals. Now recall, your area is always going to be b minus a over n times f of x sub 1 plus f of x sub 2 plus dot dot dot. So here, I first need to figure out, well, what's my width going to be of these rectangles? Well, if my interval is from 1 to 4, then my a is equal to 1, my b is equal to 4. And if I'm dividing it into 3 subintervals, then n is equal to 3. So I would have my delta x, or that width, is equal to 4 minus 1 over 3, or 1. So then my area with my left endpoints, L sub 3 here, is going to equal, again, it's going to be y b minus a over n, which is 1, times, well, now I have to figure out what is the y value of all my left endpoints. So I have this rectangle, and this rectangle. So I need to figure out what is this y value, what is this y value, and what is this y value. Well, f of 1, it looks like, is equal to 1. F of 2 is equal to 2. And f of 3 is equal to 5. So the area using my left endpoints is equal to whatever 1 times 1 plus 2 plus 5 is, and that's equal to 8. Let's do the same thing over here, but let's use right endpoints. So again, I'm looking for this area right here, but I'm going to be using my right endpoints. My delta x is still going to be the same. My delta x is still going to equal 1. So my right endpoints, r sub 3, is going to equal 1 times. Well, now I have to find all my right endpoints. So I'm looking at this rectangle here, and this rectangle here, and this rectangle here. Well, my right endpoints will be, well, this endpoint here is f of 2 is 2, plus here f of 3 is 5, plus here f of 4 is 10. So my area is going to equal whatever 1 times 2 plus 5 plus 10 is, which is 17. Let's do that again for example 2. I'm looking at the interval from 1 to 4 into 3 equal subintervals. So my delta x is still going to be 4 minus 1 over 3, or 3 over 3, which is just 1. So here I just need to figure out what my left endpoints are. Well, I'm looking for this area. So my left endpoints are here for this rectangle, here for this rectangle, and then here for this rectangle. So this endpoint is at 10, this is at 9, and then this one is at 6. So the area using left endpoints, L sub 3, is going to be whatever 1 times 10 plus 9 plus 6 is, 25. Now let's do the same thing for my right endpoints over here. So again, we're computing this area here. But now we're going to use our right endpoints. Now my right endpoints in this case are going to be this one for this rectangle, here for this rectangle, and then here for this rectangle. So this is going to be, well, this is a 9 plus 6 plus 1. So then my area for my right endpoint for this curve is r sub 3 would equal 16.
Now left and right sums are special cases of more general sums called Riemann sums.
Riemann sums allow us to find the area under the curve where the height of that rectangle can occur anywhere within the subinterval. So for a left sum, it has to be the left endpoint. For a right sum, it has to be the right endpoint. But for a Riemann sum, that point just has to be somewhere that lies between the subinterval. And this is getting us closer and closer and closer to the definite integral. Now, the thing is, if we don't have to use the left endpoints and the right endpoints, if we can use the Riemann sums and we allow the number of subintervals to be infinity, then as your width of each one of those rectangles gets smaller and smaller and smaller, you're approaching some real number I. So as you get
An infinite amount of rectangles,
your area is going to be approaching some number. So then the definition of the definite integral. The definite integral says the following. If f is continuous on a closed interval, the limit I of the Riemann sums of f on that closed interval is called the definite integral of f from a to b and is denoted as the definite integral from a to b of f of x dx. Now remember, the indefinite integral does not have letters or numbers there. The definite integral is bounded by a lower limit of integration and an upper limit of integration. The indefinite integral, you'll need your plus c's for. The definite integral provides you with the area under the curve. A couple more things before we look at examples. Now, recall when we were finding area, we said that this was our width and then our height was going to be our length for our rectangles. Now, area that lies above the x-axis is counted positively, and area that lies below the x-axis is counted negatively because those heights of those rectangles are going to be negative there. So when we're calculating area given a graph, any area that lies above the x-axis is counted positively, and any area that lies below the x-axis is counted negatively. So now let's take a look at the following examples. And we're just going to do examples 3 and 4. Go to the next page, look at a couple of the properties, and then come back and do examples 5 and 6. So it says calculate the definite integral by referring to the figure with the indicated areas. So let's draw in all of this because I didn't have a chance to put it on our graph. So just to clarify, this here is our y-axis, and this here is our x-axis. So at this point on my x-axis is A, this is B, this is 0, this is C, and this is D. And we're going to call this area A, this is area B, this is area C, and this is area D. So if I want to find the integral from 0 to c of f of x dx, what I want to find is the area from 0 to c of this graph. Well, that's area C. What is the answer for area C? In this case, that's equal to 6.80. What about the integral from b to d of f of x dx? Well, the integral from b to d is going to be the area from here, including this, and then down below. So it's going to be the sum of area B plus area C plus area D. Now recall, anything that lies below the x-axis is counted negatively, and anything that lies above the x-axis is counted positively. So therefore, this is equal to, well, the area for B is 2.13 units, but it lies below the x-axis, so we'd say negative 2.13, plus the area for C lies above the x-axis, and that is 6.80, plus the area for D lies below the x-axis. Since it lies below the x-axis, we know it's going to be negative, so that's going to be negative 4.17. And if we were to put all that in a calculator and compute the area, we'd end up with negative 2.13 plus 6.8 minus 4.17, which is 0.5. So our area would equal 0.5 units squared. All right, we're going to skip 5 and 6 until after we look at those properties, and we'll do that in the next video.